So then once we have our data collected, once we've done our experiment, now we got to say, is this really significant? Do we really believe our results? So what I mean by this is let's flip a coin. And I want to know if my penny is fair. That is 50% of the time when I flip it, do I get heads and 50% of the time tails? Or is for some reason like one side of the coin weighted and so you always get tails or you always get heads or something like that? So how do we know that a coin is fair? Well, somebody said, well, you flip a coin. Well, I flipped the coin once and I got heads. So do we know if our coin is fair or not? Do we know if it's 50% heads or 50% tails? Well, flipping it once really doesn't tell us very much because it's either going to be heads or tails, unless it does something really weird like land on its side. But assuming we only have heads or tails, flipping it once doesn't tell us very much because it's got to be one or the other. So now we flipped it 4 times, and now we got to ask, is the coin fair? Well, you would expect half the time to get heads and half the time to get tails, right? So this is a little bit weird because you're 3 and 1. A bunch of you are saying, but look, Dr. Ward, if I flip a coin 4 times and I get 3 heads and 1 tails, that's not unusual at all. I mean, it's kind of like having kids. There are plenty of families where there are 3 boys and a girl, and that doesn't mean anything weird happened. It's just the way it happened that you don't always get exactly 50-50. And this is where statistics comes in. This is where we start saying, how weird is it? But if you got a coin where you flipped it and it was like 9 heads to 1 tails, and you're like, that's not my lived experience. That coin, there's something probably kind of odd going on. I don't know that there's something kind of odd, but I'd be pretty suspicious if I got 9 heads and a tails that something really weird was going on. This just seems like it's more heads than you would get by chance. And this idea of what's more heads than you get by chance, this is the idea of statistics. So, for example, 3 heads and a tail occurs, a result that's that weird or weirder actually occurs the majority of the time, but getting 9 heads and 1 tails out of 10 only occurs less than 1% of the time. So, figuring that statistics out, we're not going to do a whole lot about it, but what we will say is, yep, there we need a way to think about, is this result typical or is this a fairly weird result? And when you go take Math 152, they start to tell you how to answer that question. We'll do a little bit of it in this class, but not that much. So let's go back and think about what we've done so far. So we made an observation. That's actually not even on this thing, but we made an observation, and that's super important in science. Then we ask a question. How do we explain this observation? We did some background research, hopefully, and construct a hypothesis, which was, how do we explain this phenomenon? We tested our hypothesis with an experiment. We analyzed the results. We do our statistics. We draw conclusions. And then we had come to the point where we either said we know we're wrong, or, and this is really important, we can't say that the hypothesis is wrong. So we didn't prove that the sunflowers followed the light. We just said that our experiment was consistent with the sunflowers following the light. They could be doing something else, but our hypothesis is consistent with that. So this is something that's a hard concept, is we are consistent, but we don't have proof. In either case, we report our results, and we're going to do that a lot in lab, and we're going to either ask more questions to try to give more credence to our hypothesis, or if we figured out our hypothesis was wrong or only partially true, we construct another hypothesis and think again. The other important words that you'll hear a lot are theory, principle, and law. These are essentially interchangeable in science, and these are the ones that mean that we have not only a hypothesis, but a whole suite of hypotheses that we have a lot of data on these related hypotheses, and all of it appears to support those hypotheses. We've gotten to the point that we can't really think of a way that this would be false. In fact, if it was false, we'd have to be doing an enormous amount of rethinking about science. So we have, for example, the law of gravity. We have the theory of evolution. These sorts of ideas, we can't prove 100% that they're right. And there's certainly ideas on the periphery of exactly how these things work that are still being argued about. But the idea of change over time, the idea that objects have a pull towards each other, these are things that we're pretty sure are right. Now, we can't prove them 100%, but pretty much they're as close to we take them as a given as we can. That doesn't mean that if we didn't find evidence that showed that evolution was wrong or that gravity didn't exist, we wouldn't take that into account and reformulate some of these theories, principles, and laws. We absolutely would. But there comes a point where there's this sort of group of hypotheses that scientists take as pretty much a given. We don't know it's fact, but it's close. A hypothesis has a whole lot less evidence than theories, principles, and laws.